Okay, hello everyone. I hope that you are all doing well. And today we are going to be talking about clustering. And in particular, we're going to be talking about two very popular methods. One is going to be the the K-means method, a very popular one. And also we're going to be talking about the K-means method. Okay? Okay, so basically this is the structure of the machine learning models that we have covered so far during the semester. Okay, so basically in machine learning we have two main categories. Well, we also have another category, but I'm not going to talk about that. We also have we have mainly or we cover mainly supervised learning techniques, and inside the supervised learning technique we cover classification and we also cover regression. Okay, and basically here I only put classifications because the idea is quite similar. Basically inside classification we cover a number of methods, very popular methods, okay, individual methods. For example, we have the K-means method, we have the decision trees, we have naive Bayes, but we also cover, for example, support vector machines, and so on and so forth. And the idea in classification is that we have we want to predict a category. Okay, for example, this picture is a dog, this picture is a cat, and so on and so forth. And when we can also have a more complex models. Okay, for example, in ensemble learning, when we have multiple, we want to aggregate we want to aggregate the power of multiple methods. Okay, so basically the idea is that we're going to have multiple models, multiple machine learning models. Okay, and then basically all of these models, they have to agree in the output. For example, this one is going to be saying that a picture is going to be a dog. Okay, this one is going to be saying that a picture is a dog as well, and this one, for example, is going to be saying that a cat, and this one could be saying that this is a dog. Okay, so basically here we have that, for example, in this toy example we have that picture, and then we pass this picture to the models. Okay, it's going to be a picture, and then the models are going to process that, and then they are going to be telling the output. This is the idea of ensemble learning methods. And in particular, a very popular technique is what we call random forest. Okay, we also covered that quickly in the last lecture in UCC. And basically, in random forest, the idea is that we're going to have all of these guys are going to be a decision trees. Okay, this is going to be decision trees, and decision trees. You can have a look at the slides that are available online. And the idea here is that we take all the samples that we have when we are building the model. We take all the samples, and then basically we are going to be selecting a subset of the samples, a random selection of all the samples. We select the random selection in order to build the model here, a random selection of the samples, and a random selection of the features, because the idea is that we want to create the trees, and we want to have different, we want to differentiate these models a little bit, because otherwise it's going to be basically quite similar models. Because if we have the same input, training input, then it's going to be similar. So that's why we have this random forest. You have been working on this a little bit during the lab, in the last week lab. And the solution of that lab is in another video. I strongly recommend that you have a look at that. Well, that's my solution. Of course, you can have different solutions. I try to have a solution that is clear and easy to understand. You can have different ways of writing your code. Okay, so basically this is about supervised learning. We can also have unsupervised learning techniques, and in particular we can have clustering techniques. We will be talking about this in unsupervised learning. We don't have that target label. The idea is that we will be using this, these methods in order to try to aggregate, to create groups, clusters with elements that are similar, that are related, that they share information, that they share important features. So basically, this is an example of the supervised learning approaches that we have been seeing so far. And then basically, as we can see here, we have a samples, a set of samples, and then we are going to be representing these samples with a set of with a vector of features, and then we are going to have the label. Okay, so we have an expert that is going to tell me, okay, this is an apple, this is a banana, and so on and so forth. In the case of unsupervised learning, we don't have those labels. We don't have that expert that is going to tell us the target label. We need to, all we have is the vector of features, and the idea is that we're going to try to create these groups with similar information. Okay, so this is one. We have the groups with bananas, and when we have the group with apples, but we don't have the labels. The idea is later on that we get a new picture, then we can see that this picture is similar to these elements that we have in the apples groups or clusters. Okay, so basically this is what we get, but we don't have the labels, and then we need to process that information. There are multiple applications of unsupervised learning techniques. Basically, the idea is that, as I was saying, we want to create cluster or groups, but we don't have that label. This is quite popular, for example, in segmentation, in bioinformatics, for those that are in the program, in the bioinformatics program. I'm sure that you know more than me about this, but it's another important application of clusterings. And basically, this is what we're going to have in order to clarify this. So basically, we don't have this supervision. We don't have this expert that is going to tell us the label of the method. So all we have is the vector of features describing the input. And we don't have the target label, and then we need to process that and create these clusters. Okay, so basically here what we are going to be using a lot, this is quite important, we are going to be using the distance and similarity between objects, okay, because that's how we are going to be creating these groups. All the groups, they must be close to, all the elements inside one group, they should be close to each other, okay, and then we need to have that information. And basically we have a number of techniques. I'm only going to be talking about the K-means and the K-method method. And basically this is the idea. Okay, we want to create these groups. We know that if this is going to be the input, then we know that this is going to be one group because they are close. They are the distance between these elements, they are going to be close. Okay, this is a second group and this is another group. So basically the idea is that the distance between elements, between samples inside the cluster, it should be small, but the distance between elements from different clusters, it should be relatively quite big, at least compared to the distance between the elements inside the group. So that's one of the ideas of these clustering techniques. Okay, so that's what I was mentioning. This is the intra-cluster distance. We want to minimize that distances because they all should be from the same group, from the same category. But we want to maximize the distance between the elements from different clusters. Okay, and this is also another very popular technique in order to identify outliers. Okay, because if we find the clusters, okay, this is one, this is another one, and this is another one. Basically, the outliers, they are not going to be inside the cluster. Well, at the end, we can associate this with one cluster, but we can see that the distances are going to be quite high compared to the elements inside the cluster. So, for example, these three guys, as we can see here, they don't belong to any of the clusters. So this is also a very popular technique in order to identify outliers. And remember that some of the techniques, the machine learning models, they are very sensible to outliers, and we need to remove that information. Okay, so this is just basically some of the reasons that we have in order to have these clusters. Okay, and I'm not really going to go into a lot of things. This is also quite important for pre-processing techniques. Okay, but I'm not going to be quite important. I'm not going to be talking a lot about that. This is one of the applications that we have for image processing. So basically, they use clustering techniques in order to identify objects inside the images. Okay, and this is actually a quite challenging part because, for example, here we see that this is one dolphin. Okay, certainly we can see that this is one dolphin, and then we have another dolphin here, but this part is like overlapping between the two, so this is a very challenging problem, but it's a very popular problem for image classification. Okay, so basically this is the idea of the of the clustering task. We want to get elements that are similar, okay, inside the cluster, with and a little bit different between elements from different clusters. Okay, so basically the information that we have, the input, that we get is just going to be basically a vector of features. This is not that different to what we have in the supervised approach. Basically, we can have real values for features. So basically, the salary of a person could be 1,000, 2,000, 3,000, and so on and so forth. We can have binary attributes, true, false. We can have categorical attributes. In this case, we can use different approaches in order to compute the distance between elements if we have categories. Okay, we have different approaches here. For example, we can use one-hot encoding in order to translate this into numerical values, and then we can use, for example, the Euclidean distance. But we can also use the Hamming distance. Remember that I talk a lot in the well, that I talk a little bit in the past. Okay, so basically we are going to be saying that the number of dimensions in the cluster is the number of features that we have in in the in the problem. Okay, and then we have different ways of computing the vector of features. So this is something that we have to take into account. Sometimes we have to maintain some properties. These are some properties of distant metrics, but for now this is not really relevant for what we want to talk today. Okay, so basically what we're going to be saying, for example, if we have a distance matrix, then we're going to be saying that we only need to compute this information in the matrix. Okay, we don't have to compute, we don't need to compute the full distance matrix because it's going to be quite expensive. And we know that the distance from the first element to the second element is going to be equal as the distance from the first one to the second one. These are the kind of properties that I was mentioning before. And sometimes we use this information in order to reduce the kind of information that we have. And basically this is going to be the matrix. Okay, so basically this is just the vector of features. This is the first feature for the first sample in my set, in my data set. The second one, the third one, and so on and so forth until the last one of the for the first sample, and then the last one for the last feature for the last sample. And this is just basically the distances that we are going to be using. Sometimes it's important to pre-compute this matrix because it's going to be more efficient when we want to do this, because we have to compute a lot of times. We're going to be computing the distances between points, between samples. Another quite important metric that is quite popular is called this Jacquard distance, which is using the Jacquard similarity. It's just basically using this equation in order to compute the distance between two elements. Okay, for example, this could be numbers, but it could be also categorical features. Okay, for example, we are going to be computing, all we have to do, for example, to compute the Jacquard similarity is that we are going to be counting. Let's say that we have two samples, and we want to compute the similarity between these two samples. Basically, the first one is going to be counting the number of elements that is the same. So for this part that we have here, the number of elements that we have here that are the same. For example, these two, they are the same, and we only have one. So basically, that's why we have here one, and then the total number of features that we have. So which is, in this case, is 6. Okay, so that's basically because this one is because they are the two elements here, they are the same, and 6 because this is the total size of the number of features. And this is for the Jacquard similarity, and to get the distance, basically it's going to be 1 minus the Jacquard similarity. This is just another way of computing similarities between objects, between samples, because now the similarity, the distance between elements is quite important because we want to get elements inside the cluster that are, remember that they are close to each other. Okay, so basically there are other very popular techniques for other popular distance metrics that we have. We have been using quite a lot Euclidean distance or the weighted distance. Okay, sometimes, for example, this weight we use 1 divided the actual distance to the power of n. This is a very popular way in order to compute the weights, but if you know a different way, that's also another approach. We can also use the Manhattan distance, which is also another alternative. There are different ways of computing the distance. So all I want to say here is that it's really important to know here the concept of distance. For example, another popular technique that was also taken into account a lot the concept of idea of the methods that we use for clustering. Basically, the idea is quite simple. Basically, we're going to say that we have n objects of samples, and then we are going to have a set of clusters. Most of the time, this is going to be a parameter, an input parameter. We will be seeing in the future how we can try to identify the value for this parameter, but we need to have an input is going to be the set of objects and or samples and the set of clusters, the number of clusters that we want to say. And basically what we want to know, what we want to identify is that each particular object or sample is going to belong to exactly one cluster. We cannot have that object that is going to be for two clusters. Okay, for example, and what we want to do is that there are different ways of doing that. Basically, one way is to compute the center of the cluster, and then all the other samples will be basically the samples are going to belong to the nearest center of the cluster. If we have one that is exactly at the same distance to the two centers, well, you can choose one at random, but that's not very likely to happen. Okay, so basically we need to know this number of clusters in advance. And we will be seeing later on a very simple approach in order to try to compute this. Okay, so the K-means algorithm, I think, is one of the most popular methods, and I strongly recommend that you get familiar with this because everyone knows this K-means approach is a really, really popular approach, and the idea is that we're going to be starting with some center of the cluster, so we need to compute the center of the cluster, as I was saying. Okay, so basically we're going to be saying that this is the center of the cluster, this is the center of the cluster, and then these are the points. Okay, and the idea is that we are going to be selecting, initially we start at random with this center of the cluster. We select the centers initially at random, and then we are going to be assigning the samples to the nearest cluster. Okay, for example, we say that this, of course, is closer to this center than to this other center that we have here. Okay, so basically what we're going to be doing with this approach is that we assign the points to the near center, and then once we have all the samples in one particular cluster, then we recalculate the center of the cluster. Okay, so that's something important that I will be showing examples of this. And what we want to, and then what we want to minimize is the distance, the total distance of to the points to the center of the cluster. Okay, for example, this distance plus this distance plus this distance. This is what we want to minimize. Okay, that's what we want to do. And then we repeat this process. Okay, basically we move the center a little bit, we reassign all the points to the center of the cluster, recompute the cluster, and so on and so forth until we cannot move the center anymore. I will be showing an example in a minute. Basically, this problem, computationally speaking, is quite hard. Basically, when you see that a problem is NP hard, it means that computationally speaking, it's going to be really difficult. It's going to take a lot of time. I'm not going to be talking about a lot about the NP hardness concept, but if you see that a problem is NP hard, it means that computationally speaking, it's going to be difficult. And for example, it means that the complexity to solve one problem is going to increase exponentially. Basically, that means that, for example, if we have a problem with, let's say, 100 samples, it's going to take, let's say, 2 hours. But if we increase that to 200 samples, that can go from 2 hours to 10 hours. And if we go increase that to 300 samples, it could go up to days, and so on and so forth. That's what we said, that the runtime can increase exponentially. And then that's something that we have to take into account. And basically what we are going to be saying is that we cannot find a solution in polynomial time. That's the idea of that. That is not feasible. Well, if we say that the number of clusters is equal to 1, then we can say that we can solve that in polynomial time. But I'm not going to be assuming that we have only one only one cluster. Okay. Basically, this is the general method, the general structure of the K-means method. It's quite a popular one. Basically, as I was saying before, we're going to be selecting, this is a parameter. Remember that K is an input parameter. And basically what we're going to be doing is that we choose the centers. K at random, we select in my space. Imagine that you have a two-dimensional space. I'm going to say selecting k random starting centers for the clusters, and then for each particular object or sample, we're going to be assigning that to the nearest center. And then what we are going to be doing, and now when we assign all the points, then what we are going to be doing is that we are going to be recalculating the center until we cannot improve anymore, until we cannot move the center. Okay, so hopefully I will be explaining this with an example, and it's going to be easier with example. There are a couple of problems with this because this is going to stop. Probably when we stop, this is not going to be the optimal solution. We call this a local optimal. Remember that I talked a little bit about this when we were talking about hyperparameter tuning a couple of weeks ago. And basically the solution that we get is not the optimal. We get local minimum, a local optimum, because we get to a point that we cannot improve anymore. But that solution is not going to be the global optimal solution, so the general optimal solution. This is a local optimal solution. Okay, so basically we can try to fix this a little bit if we restart. But I'm going to go into that in a minute, and I will be explaining a little bit the examples. Okay, so let's see this with an example. I always try to show an example, and I believe that it's going to be easier to see this with an example. Okay, so let's assume that we have these samples. Let's say that we have this in the two-dimensional space. Okay, so basically we have x and y, and these are the samples or the objects that we want to have, and then we want to identify the clusters. Okay, and let's assume that we are going to have, let's say that we have the value for k is going to be equal to 3. Okay, so the very first step is to uh, select the initial center at random for the three clusters. Okay, so basically let's assume that my random selection told me that these are going to be the center of the clusters. Okay, so this is just, it could be that this point is in another place. But okay, for now let's assume that these are going to be the initial centers for the cluster. We have 3 because initially we said that k is equals to 3. Okay, so remember that. Now what we have to do is that we need to assign all the samples or the objects to one particular cluster. Okay, for example, of course, this object is going to look for the closest cluster, for the closest center of the cluster. So for example, of course, this one is going to be assigned to this center. This one is going to be assigned to this center. All we are going to be doing is computing the distance between the sample and the center of the cluster, all the centers of the cluster. So this one to this one to this one here, and the other one, and then we keep the one that is the closest one. Okay, so basically we know that this guy is going to have these 3 samples, and this guy is going to have probably these 3 samples, and this guy is going to have these 3 samples. And then we have to move this center of the cluster. We try to move this one to the actual center, to the new center. Okay, we try to put this one here. Okay, and then we recompute. Okay, so basically this is the initial step. We select the centers of the clusters at random. Now we are going to assign all the samples to one and only one cluster, which is the center of the cluster. And as I was saying before, all we have to do is to compute the distance between the sample and all the centers. And then we're going to be using, for example, for this one here, it looks like the actual center is going to be this one because it's closer. Remember, now here the concept of distance is extremely important because we are going to be relying on this. We can initially assume that we are going to be using the Hamming distance or the Euclidean distance. That's really up to you. Sometimes it's going to be better to use the Hamming distance, and sometimes it's going to be better to use the Euclidean distance. It really depends on the problem that you are dealing with. Okay, so now we're going to be telling, as I was saying, we're going to be using actually that these are going to be the elements of this cluster, these 2 are going to be the elements of this cluster, and these 3 and all these elements are going to be the elements of the samples of this cluster. Now what we have to do is to move the center to the new center of this cluster. This one we're going to move this one somewhere there, this one we're going to move this one here, and this one probably is come somewhere here. Okay, we recalculate the center of the cluster, and now we are going to be now we are going to be seeing if we have to, if we need to move the, if we need to move points, samples from one cluster to another one. So we need to check if we need to reaccommodate, reallocate the samples from one cluster to another one. What we're going to be doing is checking the new distances, okay? Now we check if we need to move any sample from this cluster to the other one, and so on and so forth. For example, this one here, okay? This one here, we can certainly see that this center that is going to be after updating the center of the cluster, we see that it's going to be better to move this blue sample that we have here from this blue sample that we have here. We are going to be moving this to the center that we have, that we decided beforehand. That the new center here. So basically we're going to be changing the color of this one and probably this one as well. We're going to be changing because now this one is going to be closer to this one than this one. But we will be seeing. Okay. We didn't change this one here. It looks like this one is going to be close. Okay, so basically this is going to be, well, you have to recompute the distances and so on, and then you will get the actual numbers. Okay, so now we're going to be using these three. For example, here, we change this point, we move this point from the blue cluster to the red cluster. So now we need to update again the center of the cluster. And then we will be repeating this process until we cannot update anymore the center of the clusters. Okay, so basically this is what we're going to be happening here. We update, we move again the center of the cluster, and now this one is going to be closer to this one than to this one. We move so that we reallocate this point that we have from the blue cluster to the red cluster, and then now we're going to be moving the center again. And of course for this one we don't have to do anything because we are not changing anything from this cluster. We're not adding or removing any sample. Okay, so basically we follow this approach and so on and so forth until we cannot change anything else. Okay, so basically this is the general idea of the K-means method. Remember, we're going to be starting with that. All we have to do is to locate the center of the clusters. Okay, so basically the actual center of the cluster. So all we have to do at the very beginning is to randomly select the center of the clusters, and then we are going to be assigning the samples to the center of the cluster. Once we get the groups, the clusters, we move the center, the previous center, to the new center of the cluster for all the groups, and then we try to see if it would be better to move one sample from one cluster to another one, and then we repeat this process until we cannot change. Basically, these are some examples of different executions, because remember that this relies a lot in the original, in the randomly selected starting point. Okay, let's say that these are the points. Okay, and depending on how I select how we select the initial point, the random initial point, we're going to be getting this or this. Okay, basically we have the same number of clusters, but depending in the location of the random initial position of the centers, we get to one solution or to the other one. Remember, this is what I was mentioning a few minutes ago about the local optimum. We don't get, this is a heuristic approach. Okay, so we're not going to get the actual optimal. Here, this is going to be the optimal solution, but this is not going to be this is a suboptimal solution. But yet, it all depends. It really depends on the actual initial points of the cluster, the random initial points of the cluster. Okay, so basically we are going to be getting what we call a local optimum, but the actual time is going to be quite quick. You will be seeing that the execution time of this is going to be really quick. We are not going to be spending a lot of time. And this is actually going to be sensible a lot to the outliers, because if we have one point that is really far from the center, that's going to move the center. Okay, imagine that we have this point here. Okay, we have all these samples here. Okay, and this is going to be one cluster. Okay, all this belongs to one cluster. So because we have this gone very far, so the center is going to be more or less here. And but we can clearly see that this is an outlier. Okay, basically the center should be somewhere here, and this is an outlier. This is the problem with, well, one of the problems that we have with this approach. Okay, so basically now we are going to be seeing how what's the problem with these local optimums. And basically, let's assume that this is we have this data set, and then we want to identify three, the k is equals 3, so we want to identify three clusters. And let's say, well, here visually we can really see that we have three clusters, okay, but for the computer it's a little bit more difficult. Okay, so basically the very first step is to identify the centers. So basically, if by random chance we decide that this is going to be the center, this is going to be the second center, and this is going to be the third center, basically, of course, we are going to try to create the points based on this. Okay, so basically at the end what we are going to end up doing is that we are going to be separating this into one cluster, this into another cluster, and all these are going to belong to one cluster, because it really depends, it really relies a lot in the starting position of the random location of the clusters. Okay, of course, we can try to have a look and try to locate those depending on the density, the location of all the samples, but it's going to be a little bit difficult. There are some ways in order to deal with this problem of the local optimum. What a very popular approach. This is the one of the main disadvantages of the k-means. But how can we solve this problem or try to alleviate the problem a little bit more? Basically, what we have to do is that we can try to use these random restarting the algorithm. So basically, the idea is that we try once, and then we get one solution, and then we try again with a different random seed. Okay, so basically what is going to happen is that it's going to put the centers in a different location. And then we repeat this multiple times until we get to a solution that we are happy enough. For example, in this example, in here, let me just quickly erase this. Basically, okay, no, okay, basically here in the very first time that we execute this, that we try to get the centers, because this is a random selection, well, we get one here, another one here, and the other one here, because of the random choice. But the next execution, because remember what we try to do is that we solve these ones, we keep that solution, and then we re-execute with different uh, random locations. So basically, hopefully, because if we are going to be doing this uniform random location of the clusters, so the next time, for example, the center is going to be here and not here, and this is going to, and now we are going to have the three clusters that we are looking for. So that's why we try to keep this a uniform selection of the clusters. Okay, so basically this is just, and also remember another important inconvenience of this problem that we have is that it's sensible to outliers. So we can see here that we have two main disadvantages of the k-means method. One, that is going to be depending on the initial location of the clusters, we can try to alleviate, to partially solve these problems using restarts. This is one potential solution, but it's going to be still quite sensible to outliers, and we need to keep that approach in mind. And another situation that we have to take into account is that the center of the cluster is going to be is not the center of the cluster is not a point in my sum in my is not any point from my training set. Okay, and that could be a problem. Okay, because sometimes we want to rely in that particular center of the cluster in order to deploy my solution. And then I will be basically what we're going to be talking about is about the k-means method a little bit in 1 minute. Another important difficulty, another difficulty that we have with this k-means method is that we need to identify the value of k. this is a this is going to be a problem, and we will be seeing in a minute a very popular method for defining this k, the value of k.